Hello everyone. Thank you for joining us today for the presentation of our paper titled CAP, Robust Point Cloud Classification via Semantic and Structural Modeling, which has been accepted by CVPR 2023. This research was conducted by the White AI group at School of Computer Science of Fudan University. Our presentation begins with an overview of CAP, our comprehensive defense framework for training robust point cloud classification models against adversarial attacks. CAP enhances the semantic and structural modeling abilities of existing classifiers while providing a robustness certification algorithm for potential attacks. In this slide, we demonstrate the overall framework, highlighting the attention-based feature pooling module and dynamic contrastive learning procedure we propose. Before delving into the detailed design of CAP, let us first shed light on the adversarial threats the point cloud classifiers face. The task of point cloud classification has gathered significant attention due to its relevance in autonomous driving applications. In this task, a deep neural network is trained to recognize a sample X comprising a set of endpoints with their respective 3D coordinates and assign a corresponding class label. However, it is widely recognized that neural networks are vulnerable to adversarial attacks. These attacks involve manipulating inputs slightly to induce unexpected misbehavior in a classifier, potentially leading to severe consequences in real-world scenarios. For point cloud data, various adversarial attacks have emerged, each employing distinct types of perturbations, including addition, shifting, and deletion of points. These attacks may also possess diverse properties, such as the presence of outliers, missing parts, or shaping variance. Existing defense mechanisms have struggled to address these challenges effectively. For example, well-known adversarial training-based defenses are proven to be ineffective against unseen attacks, while recovery-based defenses fail to restore shaping variant adversarial examples to their original form. In this study, we were motivated by the observation that adversarial examples often preserve the semantic and structural information of normal samples. We also noticed that existing classifiers tend to focus on limited segments or local features of input point clouds. To address these limitations, we introduced CAP, which stands for Contrastive and Attentional Point Cloud Learning Framework. With the CAP framework, we have designed an attention-based feature pooling module. This module enables the classifier to automatically pay attention to crucial parts of a point cloud, thereby capturing essential information more effectively. Additionally, we leverage a dynamic contrastive learning paradigm to encourage the separation of point cloud features from different classes, enhancing the classifier's discriminative power. Moreover, we propose an algorithm to theoretically certify the robustness of a classifier. This algorithm is based on manifold learning and extreme value theory, allowing us to provide a measure of classifiers' resilience against adversarial attacks. For the detailed design of the attention-based feature pooling module, we replaced traditional max pooling in current classifiers with class-wise attention operations, computing an attention score for each point with respect to each class. These attention scores are later used to aggregate point features. Additionally, we incorporate an extra convolution layer to obtain a global point cloud feature, capturing a holistic representation of the input. In the context of dynamic contrastive learning, we utilize the commonly used triplet loss function to separate sample features across distinct classes. To achieve a more effective separation, we introduce the margin loss, which restricts the maximum triplet loss within the training batch. This constraint helps to enhance the discriminative power of the learned features. To ensure a stable training process, we introduce the dynamic training loss, which balances the margin loss using the value of the average triplet loss, denoted as L subscript O. This approach helps to maintain a suitable learning rate and ensures that the training process converges smoothly. In terms of robustness certification, we begin by considering that samples belong to different classes lie on corresponding manifolds. Drawing from the principles of manifold learning, we can estimate the distance between samples by calculating the Euclidean distance between the extracted features. obtained through the classifier. As a result, for robustness certification, we only need to estimate the maximum feature bias within a class and the median feature distance between classes. To address the challenge of computing the supremum and infimum, we employed principles of extreme value theory to estimate the two series of distances. This approach allows us to estimate the maximum and minimum distances reliably. Consequently, the certified probability between two classes can be determined by identifying the crossing point of the two estimated distances. Extensive experiments have been conducted on two widely used benchmark datasets using three classical-based classifiers. Our evaluation encompasses 9 attack baselines, spanning from conventional attacks to more recent shipping variant attacks. In addition, we have compared our CAP framework against 7 defense methods, including adversarial training-based approaches and recovery-based methods. Sufficient quantitative results state the effectiveness of our proposed CAP. However, due to the time constraints of this presentation, we'll focus on highlighting a few key qualitative results. Firstly, the plot on the left demonstrates that with the integration of CAP, classifier can effectively separate features, thereby enhancing its robustness. Moving to the top right corner, we present two heat maps that showcase the coherence between the certified robustness results and the empirical attack success rates. These heat maps highlight the correlation between the certified robustness of CAP and the actual performance of the classifier in defending against adversarial attacks. Lastly, the bottom right figure illustrates how CAP enables classifiers to emphasize different parts of the point cloud based on different classes. This capability is crucial for capturing class-specific information and enhancing the classifier's ability to make accurate and precise predictions. In summary, our research emphasizes the preservation of key characteristics in adversarial attacks and introduced CAP as a framework to enhance modeling of semantic and structural information in point clouds. CAP incorporates attention-based pooling, dynamic contrastive learning, and an effective robustness certification algorithm. For future work, we aim to validate CAP on a broader range of base classifiers and explore its applicability in other point cloud-related tasks like object detection and segmentation. Additionally, extending CAP to different domains and data modalities holds potential for enhancing robustness and security in other machine learning systems. That's all for the presentation today. Thank you for listening, and feel free to scan the QR code here to visit the website of our group.